Hi, this is Kate, and we're solving systems by elimination. Solve the system. 6x minus 3y equals negative 11. 3x plus 3y equals 17. We're looking for two numbers, represented by x and y, that make both of these equations true. So we could try some things over here in the blue. Let's say if x is 1, what would y be? Well, we're solving, we'll subtract the 6, divide by negative 3, y would be 17 thirds. So let's write that down. Okay, what about if x is 1 in the red equation? 3 times 1 is 3, subtract the 3 from both sides, divide by, oh shoot, it's not 17 thirds. So when x is 1, that's not the solution. We would call this guess and check. How about if x is 0? 6 times 0 is 0, divide both sides by negative 3. In the blue, when x is 0, y is 11 thirds. Well, how about in the red? Oh, we'll divide by 3, and we get 17 thirds. Okay, so when x is 0, that's not the answer. We could be at this for a while if we're just plugging in numbers and hoping that we get lucky. We could represent all the x's and y's that make each equation true by using a graph. So this red line represents all the xy pairs that make the red equation true. If we graphed all the xy pairs that made the blue equation true, which line is the correct graph? Can you use your line graphing skills to figure that out? The correct graph would be choice B. Probably the easiest thing to do would be to subtract 6x from both sides. Here we're getting the y by itself. Now we'll divide both sides by negative 3. So now we can see the slope of the line we want is positive 2, and its y-intercept is approximately 3.67. That's really 3 2/3. So the blue graph are all the points that make the blue equation true. We're looking for the point that makes both equations true. So we want to isolate the point that lies on both the blue line and the red line. That's going to be the point where they intersect. Can you look at the graphs carefully and decide which xy pair is the best solution to this system? Seems like the y-coordinate is exactly 5, but the x-coordinate is somewhere between 0 and 1. It's really hard to tell from this graph what exact value of x is going to make both of the equations true along with the 5. Solving by graphing becomes difficult when the solutions are not integer values. There's an algebraic technique we can use called substitution, where we get one letter by itself in one equation. So over here in the blue equation, I'm going to get the x by itself. So I added 3y to both sides, and then I'll divide both sides by 6. Then if we replace the x in the other equation with that expression, 3y minus 11 all over 6, we end up with an equation that only has y's in it. And we could theoretically solve this equation for y, but with that big fraction in there, this is kind of a mess. Substitution will always work, but it's not always pretty. So I want to introduce you to a third way to solve systems of equations. Remember, the first way was graphing, the second way was substitution. There is one more technique we can use. I'm just going to slide this one over here for now and ask you a simple question. If I tell you that a equals 3 and b equals 2, what could you conclude about a plus b? You would have to conclude that a plus b is 3 plus 2, or 5. When we add equal things to equal things, we get equal things. Now back to our problem. Look at what's going to happen if we add these two equations together. So I added up everything on the left and everything on the right. Well, within these two equations on the left-hand side, there's a negative 3y and a positive 3y. Those are going to add up to 0 y's. If I add up the left and add up the right and combine like terms and simplify, wow, look at what we get. 9x equals 6. Now I can easily figure out, dividing both sides by 9, that x is exactly 6/9. We could also reduce that to 2/3, and we have the x value of our solution. We still need to find the y value. So I'm going to substitute 2/3 in for x in one of the equations. It doesn't really matter which one you choose. 3 times 2/3 is just 2. We'll subtract 2 from both sides and then divide both sides by 3. The y-coordinate is 5. And that's exactly what we expected from the graph. The x-coordinate is something between 0 and 1, and the y-coordinate is 5. Elimination was an easy way to figure out that the x-coordinate is exactly 2/3. That's probably not something we would have guessed way back at the beginning, right? Would you ever guess 2/3? Probably not. We used the red equation to come up with the 5, so we can feel pretty confident about that. But it's always nice to plug your answer back into the original equation and make sure that it works just in case you made a mistake. 6 times 2/3 is 4, and -3 times 5 is -15, and then 4 minus 15 is -11. So we know that our solution works. Okay, this is a different problem, and there's a little bit of a wrinkle on this one. In the previous problem, when we lined up the two equations, the -3y and the +3y added up to a 0. That allowed us to eliminate the y's and write an equation that only had x's in it. But if we look at our new problem, if I add these two equations together right now, 5x and 3x are going to add up to 8x. 2y and -y are going to add up to +1y. So this system is not quite as convenient as our first example. But first I just have a simple question for you. If I tell you that a equals 3, what could you tell me about 2 times a? You would know that 2 times a is 6. If I have equal things, it's perfectly acceptable to multiply both sides by the same thing, and we still get equal things. Well, look what's going to happen over in our problem if we multiply both sides of this bottom equation by a 2. You see what's going to happen there? The -y times 2 is going to cancel out with the +2y when we add them together. 2 times 1/2 is 1. And to multiply the whole right side by 2, I need to distribute that 2. So 2 times 3x is 6x. -y times 2 is -2y. I'm just going to copy over the red equation and line things up to make combining them a little bit easier. Now, when we add the two equations together, the left sides and the right sides, we'll eliminate the y's because the 2y and the -2y add up to 0 y's. So what are we going to get if we add these two equations together? On the left, 10 plus 1 is 11, and on the right, 5x and 6x adds up to 11x. The 2y and the -2y add up to 0 y's, so we don't have to write that. Well, isn't this a beautiful thing? 11 equals 11 times x. X must be 1. Would you please plug that 1 back in for x into either equation and figure out the solution's y-coordinate? You should have gotten 5/2 for the solution's y-coordinate. If you didn't, go back and check your work carefully. So we think we know the solution to this system. We think that when x is 1 and y is 5/2, it makes both of these equations true. It's important to plug the solution back in and check, just in case we made a mistake. So in the blue equation, we'll substitute in a 1 for x and 5/2 for y. 3 times 1 is 3. Another way to write 3 is 6/2. And 1/2 equals 6/2 minus 5/2. That makes sense. In the red equation, we'll substitute in a 1 for x and a 5/2 for y. 5 times 1 is 5, and 2 times 5/2 is also 5. 10 equals 5 plus 5, which is true, so we know we found the solution to the system. This is Kate, and you've been solving systems by elimination.